8,500 horsepower. The most powerful freight locomotive an American railroad had ever put on the rails. Union Pacific's gas turbine could drag 700 cars across the worst mountain grades in the West. But at full throttle, it swallowed fuel at 15 gallons per minute, 1,000 gallons every hour. Even with a purpose-built tender hauling 24,000 gallons of heavy oil behind it, this machine could drink itself dry before the day was out. Union Pacific had built a locomotive whose thirst could outrun its own usefulness. The real question was never whether it had enough power. It was whether anything could justify the cost of keeping it fed. The physics of railroading dictate a hard boundary. A locomotive can only pull what its traction motors can grip, and it can only run as far as its fuel supply allows. When Union Pacific introduced the third-generation gas turbine electric locomotives, they attempted to bypass these constraints. They built a colossal power plant designed to conquer the steepest climbs of the American West. But in heavy industry, every mechanical leap demands a compromise. To achieve such extreme pulling capacity, the turbines required a volume of fuel that challenged the physical limits of the railway itself. This created an unsustainable loop. To satisfy the turbine's aggressive appetite, the railroad had to couple a specialized tender behind the locomotive. This tender, carrying thousands of gallons of heavy oil, added dead weight to the train, weight that the turbine itself had to pull. The very machine built to maximize freight capacity spent a significant portion of its strength merely dragging its own sustenance. This balance of trade-offs meant that the turbine's main advantage, its concentrated power, directly engineered its own defeat. Traditional diesel locomotives, though less powerful per unit, could idle quietly and conserve fuel on level ground or during delays. The turbine could not. It ran hot, loud, and incredibly thirsty, regardless of whether it was climbing a mountain or waiting on a siding. The operational math quickly turned sour. By prioritizing pure power density over fuel economics, Union Pacific had built a mechanical giant that threatened to consume the very profits it was designed to generate. Between 1958 and 1961, Union Pacific accepted delivery of 30 colossal 3-unit machines that would redefine the limits of rail power. These were the third-generation gas turbine electric locomotives, the largest and most ambitious experimental fleet ever to run in North America. Stretched out at over 165 feet in length, these multi-unit giants were built specifically to master the grueling grades of the overland route, climbing through the high mountain passes of Wyoming and Utah. They quickly earned a nickname that perfectly captured their overwhelming presence: the Big Blows. The name was born from the sound they made. Unlike the rhythmic chugging of a steam engine or the low thrum of a diesel, these locomotives utilized an aircraft-style turbine that produced a deafening, high-frequency jet exhaust. The roar was so intense it could be heard for miles across the open plains of the American West, shaking the ground and rattling windows in every town they passed. For over a decade, this fleet of 30 units served as the ultimate symbol of the jet age optimism that swept the post-war era. Union Pacific placed them at the very front of their heaviest freight runs, pitting raw turbine power against the rugged terrain of the Wasatch Range. Even today, they remain a legendary chapter in railroad history, remembered for their sheer size, their deafening roar, and their standing as one of the boldest mechanical gambles in the pursuit of absolute power. In the late 1950s, Union Pacific faced a geographic challenge unlike any other American railroad. Its primary main line, the overland route, stretched across vast, sparsely populated expanses between Council Bluffs, Iowa, and Ogden, Utah. To move heavy freight over this long corridor, trains had to conquer the grueling Wasatch Grade, a 65-mile climb with a sustained 1.14% incline. As the railroad retired its final steam locomotives by July 1959, including the massive 4884 big boys, it needed a modern successor capable of matching that raw, concentrated pulling force. The diesel-electric locomotives of the era were limited, typically producing only 1,500 to 2,000 horsepower per unit. Hauling a heavy freight train over the mountains required coupling 3 or 4 of these diesel units together. This multi-unit setup increased mechanical complexity, multiplied the points of potential failure, and demanded extensive maintenance and crew coordination. Union Pacific's pursuit of gas turbine power was a calculated response to this operational bottleneck. The railroad was under constant pressure to move larger tonnages on faster schedules. If a single turbine locomotive could generate 8,500 horsepower, matching the tractive effort of an entire block of diesels, the railroad could simplify its operations and cut down on train handling times. On paper, the extreme power-to-weight ratio of the turbine offered the ultimate strategic tool to conquer the mountainous terrain of the American West. The mechanical concept of the gas turbine electric locomotive relied on a straightforward engineering premise. In a conventional diesel-electric locomotive, power begins with a reciprocating internal combustion engine. Pistons move up and down inside cylinders, turning a heavy crankshaft. This complex assembly of valves, pistons, and connecting rods drives an electrical generator, which then sends current to the traction motors on the wheels. It is a highly reliable system, but it is mechanically dense, filled with hundreds of moving parts that wear down over time. The gas turbine offered a simpler alternative. Instead of reciprocating pistons, the turbine utilizes a continuous, axial flow process. Air enters the front of the engine and is compressed by a series of spinning blades. This highly compressed air is forced into a combustion chamber where fuel is continuously injected and ignited. The resulting high-energy gas expands rapidly, rushing through turbine stages to spin a single central shaft at thousands of revolutions per minute. This rotating shaft directly drives the main generator, producing the electricity needed to power the traction motors. To Union Pacific's engineering department, this layout represented a major mechanical advantage. By eliminating pistons, valves, and reciprocating mass, they could pack massive generating capacity into a far more compact space. On paper, a single rotating shaft meant fewer moving parts, reduced mechanical wear, and an unmatched power-to-weight ratio. It was a clean, elegant solution that promised to bypass the physical and mechanical limitations of the reciprocating diesel engine entirely. When General Electric delivered the final 30 gas turbines to Union Pacific, they introduced a specification that shattered every existing benchmark on American rails: 8,500 horsepower from a single prime mover. At a time when the most advanced diesel-electric locomotives struggled to produce 1,800 to 2,000 horsepower, a single third-generation turbine offered the concentrated pulling capacity of an entire 4-unit diesel consist. This massive output was generated by a General Electric Frame 5 gas turbine, spinning at a continuous 3,600 revolutions per minute. The single-shaft power plant turned a main generator that delivered electricity to 12 traction motors across 2 giant CC wheel arrangements, translating raw rotational force into 240,000 pounds of starting tractive effort. The sheer physical scale of the machine matched its internal capability, dominating the head end of Union Pacific's hotshot freight runs with an aggressive, singular authority. On the main line, this unparalleled tractive power gave a single locomotive the strength to move heavy transcontinental tonnage over the steepest mountain grades without the need for mid-train helpers or complex multi-unit communication systems. To railroad executives and industry observers, in the late 1950s, this extreme concentration of power represented the logical future of rail transport. It promised to increase track capacity, drastically reduce train handling times, and simplify maintenance schedules by replacing hundreds of reciprocating diesel pistons with a single, elegant rotating shaft. During this brief peak of jet age optimism, the 8,500 horsepower turbine stood as the absolute summit of heavy freight technology, making contemporary diesel fleets look obsolete before they had even fully taken over. The theoretical efficiency of a gas turbine relies on a specific thermodynamic condition. It must run hot and fast, held near its maximum design speed of 3,600 revolutions per minute. At full throttle, the General Electric Frame 5 turbine converted fuel to tractive effort with massive capacity. But a railroad mainline is not a sterile laboratory, and a freight train cannot run at maximum power indefinitely. Real-world operations force constant variations in speed and power. Trains must slow down for speed restrictions, wait on passing sidings, coast down mountain grades, and idle in congested yards. In these part-load conditions, the turbine's mechanical advantage turned into a severe liability. Unlike a reciprocating diesel engine, which can idle at low RPM and consume very little fuel, a gas turbine is a continuous flow machine. To keep its axial flow compressor spinning and maintain operating temperatures, the turbine had to burn several gallons of fuel every minute, even when the locomotive was completely stationary. This thermodynamic reality created a costly operational trap. The very design that delivered 8,500 horsepower on steep climbs continued to consume fuel at a high rate during unavoidable delays. When pulling a heavy load up the Wasatch grade, the economics functioned. But the moment the train crested the summit and began to coast, or was held in a siding for a passing train, the turbine continued to drain its fuel tender for zero tractive return. The machine was built for an operating world it could not stay inside. To make this massive power plant economically viable, Union Pacific made a calculated compromise on fuel. Standard diesel was refined, clean, and expensive. Instead, the railroad chose to feed the turbines with number 5 heavy fuel oil, often called Bunker B. In the late 1950s, this heavy residual oil was essentially a waste product of the petroleum refining process, costing as little as 1 cent per gallon. On paper, burning a cheap industrial byproduct to generate thousands of horsepower looked like financial genius, allowing the turbines to run at a fraction of the fuel cost of a contemporary diesel fleet. But this economic shortcut came with a physical catch. At room temperature, Bunker B is thick, highly viscous, and behaves more like tar than liquid fuel. It cannot be pumped or atomized in its raw state. To make it flow, the railroad had to heat the fuel to 200 degrees Fahrenheit before it could even enter the combustion chambers. This required installing dedicated steam and electric heaters inside the locomotives and tenders, as well as maintaining heated storage tanks and transfer lines at every fueling depot. This thermal requirement turned the simple turbine concept into a maintenance burden. If a heater failed in the freezing mountain air, the fuel solidified, starving the turbine and causing immediate flameouts. The heavy oil also left thick, carbon-rich deposits and ash that eroded turbine blades and fouled fuel injectors over time. What began as a rational fuel-saving strategy introduced a complex, high-maintenance web of heaters, pumps, and constant cleaning. To keep this colossal turbine supplied with heated fuel, Union Pacific had to look beyond the physical boundaries of a standard locomotive frame. A standard internal fuel tank lacked the necessary capacity. The solution was a massive, dedicated fuel tender coupled directly behind the power units. These were rebuilt Class 24 CGTE tenders, originally salvaged from retired steam locomotives and heavily modified for turbine service. Each tender carried a nominal capacity of 24,384 gallons of heavy oil. When fully loaded, this rolling tank weighed over 300,000 pounds, adding a massive physical load to the train before it even departed. The locomotive had outgrown the normal physical limits of a single railway vehicle, requiring a mobile fuel depot to remain operational. Yet even this enormous reservoir failed to eliminate the machine's refueling dependency. At full throttle, the 8,500 horsepower turbine consumed fuel so rapidly that even 24,000 gallons offered limited range on the grueling climbs of the overland route. To keep these giants running, Union Pacific established a synchronized network of refueling points and standby tenders across Wyoming and Utah. Crews routinely executed rapid tender swaps at division points like Cheyenne and Ogden, uncoupling empty tanks and rolling fresh, preheated tenders into place. The workaround kept the big blows moving, but it exposed the central contradiction of the design. To haul freight across the West, the turbine first had to haul a massive heated lake of its own fuel. The mathematical reality of a railroad is defined by the duty cycle, not the specification sheet. While a diesel locomotive's fuel consumption scaled efficiently with its workload, the gas turbine demanded a constant baseline of fuel just to keep its internal compressor spinning. At a standstill in a yard or idling on a passing siding, the turbine consumed roughly 100 gallons of fuel every hour. The moment the engineer opened the throttle to full power, that consumption rate surged to 15 gallons per minute, 900 gallons per hour. Across a typical freight run on the overland route, this massive appetite translated into an average consumption of 14.71 gallons of heavy oil for every mile traveled, even at a modest average speed of 33 miles per hour. This operating math quickly shattered the turbine's theoretical efficiency. Heavy freight railroading in the American West was defined by delays, waiting for opposing traffic on single-track main lines, crawling through congested terminals, and slow climbs behind slower trains. Every minute spent waiting on a siding or creeping through yard limits drained the tender for zero tractive return. To maintain this high-volume throughput, Union Pacific had to treat these locomotives like short-range interceptors. They could not function as long-haul heavy haulers. The intense burn rate turned refueling into a constant, logistically punishing constraint. Instead of running seamlessly across divisions, the big blows required precise, frequent refueling stops that disrupted yard schedules and added high operating overhead. The machine built to simplify mainline power had instead bound the railroad to an inflexible, logistical loop. The physical presence of the third-generation turbines extended far beyond their massive size and voracious appetite for oil. They announced their arrival miles before they could be seen, operating at a continuous 3,600 revolutions per minute. The General Electric turbine produced a high-frequency, screaming exhaust that regularly exceeded 150 decibels. This acoustic onslaught earned them their lasting nickname, the Big Blows. It was not a rhythmic chugging or a low-end rumble, but a deafening jet engine roar that literally shook the ground. For the crews inside the cab, the noise was a constant physical assault. Engineers and firemen reported feeling the intense vibrations deep in their chests, a sensation that turned standard shifts into grueling endurance tests. The intense noise and constant high-frequency hum caused severe physical fatigue, making the insulated cabs feel less like control rooms and more like high-vibration pressure cookers, where clear communication was nearly impossible. But the burden did not stop at the right-of-way. As these multi-unit giants screamed through towns along the overland route, they rattled windows, cracked plaster, and disrupted daily life for miles on either side of the tracks. The public backlash was immediate and severe. Densely populated areas became hostile territory for the locomotives. Municipalities began passing noise ordinances specifically targeted at the turbines. And major cities like Los Angeles became effectively off-limits to the machines. This acoustic signature turned a post-war engineering triumph into a daily public relations disaster, severely restricting where Union Pacific could actually run its most powerful assets. When Union Pacific built its turbine fleet, the entire program rested on a single, central economic foundation: the cheapness of the fuel. In the late 1950s, number 5 heavy oil cost roughly 1 cent per gallon. At full throttle, burning 15 gallons every minute or 900 gallons per hour cost the railroad just $9 an hour in fuel to run. This low price made the turbine's massive appetite financially tolerable, easily offset by the high tonnage the machine could haul over the grades. But during the 1960s, the global oil market began to shift. The price of heavy fuel oil steadily rose, eventually reaching 5 cents per gallon and climbing higher. Because the turbine's consumption rate was so extreme, even minor price changes had a multiplying effect on operating budgets. At 5 cents a gallon, the hourly fuel cost for a single big blow surged from $9 to $45. Against this new reality, the original cost logic collapsed. A comparable diesel consist, burning 200 to 300 gallons of fuel per hour, suddenly became far cheaper to operate than the turbine. Union Pacific's internal accounting revealed that a single turbine required $20,000 to $25,000 a month in fuel alone, which was 3 times the cost of a diesel fleet of equivalent power. The extreme burn rate, once considered a manageable operational trade-off, became an unsustainable penalty. Every mile traveled became a direct drain on profitability, transforming the railroad's most powerful strategic tool into a multiplying liability. In the post-war era, oil refineries underwent a massive technological shift. Historically, heavy residual oils, like number 5 bunker B, were treated as low-value waste, sold cheaply just to clear storage space. But the rapid rise of the modern petrochemical industry changed the chemistry of refining. New processes like catalytic cracking, visbreaking, and coking allowed refineries to break down these heavy, viscous oils into high-value chemical feedstocks. These feedstocks became the basic building blocks for manufacturing plastics, synthetic rubber, and asphalt. The fuel that kept the gas turbines economically viable was suddenly a highly prized industrial raw material. Refiners realized they could generate far higher profits by selling residual oils to chemical plants rather than marketing them as low-margin locomotive fuel. The vast, cheap supply that Union Pacific had built its entire turbine strategy upon began to evaporate. This external market pressure transformed the economics of the overland route. Union Pacific was no longer purchasing an unwanted byproduct. The railroad was now competing directly with the explosive post-war consumer economy for the exact same barrel of oil. As refineries reconfigured their facilities to boost high-value chemical yields, the supply of inexpensive heavy oil dwindled. The economic foundation of the big blow collapsed. This defeat came from a massive outside industrial shift that priced the locomotive out of existence, independent of any internal railroad logistics or mechanical failures. During the decade of turbine operations, the reciprocating diesel locomotive did not stand still. Electromotive Division and General Electric steadily closed the horsepower gap, introducing newer, high-horsepower models like the 3,600 horsepower Electromotive Division SD45 and the 5,000 horsepower General Electric U50. These machines offered an advantage that the turbines could never match: a highly adaptable efficiency curve. While a turbine's thermal efficiency collapsed to around 15% under part load or idling conditions, contemporary diesel engines maintained a flat thermal efficiency of 30 to 35% across nearly their entire operating range. This thermal flexibility transformed the practical realities of everyday freight service. It consists of multiple diesel units easily adjusted to variable mainline speeds, coasting or idling during delays, with minimal fuel penalty. If a train required less power on level ground, the crew could simply isolate and shut down individual diesel units to conserve fuel. An operational impossibility with a single-shaft turbine. As diesel reliability and power output climbed, A combination of 3 or 4 modern diesel units easily match the 8,500 horsepower tractive effort of a big blow, without requiring specialized maintenance networks. If a single diesel engine suffered a mechanical failure on the line, the remaining units in the consist could still haul the train safely to its destination. The railroad no longer faced a forced choice between concentrated horsepower and operational economy. The diesel locomotive had evolved into a tool that delivered both, rendering the massive, single-shaft turbine obsolete by proving that adaptability under real-world conditions mattered far more than raw, unyielding power density. By the late 1960s, Union Pacific began systematically scaling back its turbine operations. The 33rd generation giants, which once dominated the high-speed overland freight runs, found their active territory shrinking to a narrow corridor between Cheyenne and Laramie. The railroad quietly sidelined individual units as they reached major overhaul intervals, choosing not to invest fresh capital into a propulsion system with such punishing fuel requirements. Most of the fleet had logged over 1 million miles of hard service, but their physical components were wearing out alongside their economic viability. On December 26, 1969, Locomotive number 12 pulled its last regular freight assignment through Granger, Wyoming, marking the final run of a big blow in active service. 2 months later, in February 1970, Union Pacific formally cleared the remaining turbines from its active roster. The railroad sold most of the fleet back to General Electric, or sent them directly to scrapyards, where their heavy steel frames were cut down and their specialized generators were salvaged. Of the 30 massive machines built to climb the Wasatch grade, only 2 escaped the scrapper's torch. Locomotive number 18, built in August 1960, was stored for decades before its donation to the Illinois Railway Museum in 1992. Its sister unit, Locomotive number 26, found a permanent home at the Utah State Railroad Museum inside the historic Union Station in Ogden. Today, these silent survivors, coupled to their massive residual fuel tenders, stand as physical monuments to a brief era when raw power was pursued at any cost. The big blows remain memorable because they were both technically brilliant and operationally impractical. They did exactly what they were designed to do. They generated unmatched tractive effort and conquered the steepest grades of the overland route. Their ultimate retirement was not a failure of raw mechanical power, but a fundamental failure of fit. For a specialized propulsion system to succeed, every variable in the wider system must align. The fuel supply, the operating patterns, and the external energy markets all had to cooperate. When those variables shifted, the economic foundation of the entire program collapsed. A different fuel or more stable market conditions might have altered the operating math temporarily, but they could never erase the turbine's core part load problem. The thermodynamic penalty of a continuous flow engine was permanent. A locomotive that must consume a massive baseline of fuel just to keep its axial compressor spinning at a standstill will always struggle against the real-world delays of freight railroading. The lasting lesson of the gas turbine era is that transportation technology cannot exist in a vacuum. A machine does not run on a test stand. It runs within a complex, shifting industrial ecosystem. To survive, it must withstand the pressures of the entire system around it, from fuel supply chains to the continuous evolution of its rivals. The turbines were ultimately defeated not by their engineering limits, but by the basic economics of the very system built to keep them fed. Today, as transit races toward alternative fuels, the turbine's legacy looms large. It proves that engineering triumphs are always bound by operational reality. Raw power means nothing without sustainable logistics. As we design tomorrow's transport, the lesson remains: efficiency always wins. What do you think of this colossal machine? Let us know below.